Students, this is a calorimetry introduction part. Uh, Before that, you need to understand what exactly heat is. We will study in depth uh, in coming weeks in KTG and thermodynamics, but still, what I would like to add is heat is the form of energy only in flow. Means when you are transferring heat from a hot body to cold body, only then you will realize the term heat. See, what is the cause of transfer of heat? The cause for the transfer of heat is simply because temperature difference. Now you see here, you have body A, body B. So relatively A is hotter than B. So heat transfer is possible from A to B. That is the reason why you need to use the form of energy or the name heat only during transit. Once the transfer is done, that is, once it is transferred, that will become internal energy of the receiving body. So there is a clarity, or you need to distinguish these two terms, heat and internal energy. Heat is only, I should say, it is so and so amount of heat is transferred from body A to body B. It's not internal energy transferred. Whereas the moment you transfer heat, maybe the internal energy of the other body might rise, may increase. So therefore, heat is only the term that you need to use in transit. The unit for heat in SI system is as well joule, whereas the unit of heat energy is calorie in CGS system. Actually, if prior to some 1800 odd, that period, it was not identified that heat is a form of energy. I repeat, heat was not recognized as a form of energy. There is a fluid type of concept. Heat was, it was supposed to be something needed to raise the temperature of a body or to change its phase. It was supposed to be some fluid like picture. At that time, calorie was defined as the unit of heat. So later on, as the science proceeds, the calorie is defined as the amount of heat needed to raise the temperature of 1 gram of water, 1 gram of water from 14.5 degrees centigrade to 15.5 degrees centigrade at normal atmospheric pressure. 1 calorie, technically speaking, 4.186 joules. But see, for practical problem purposes, most of the problem purposes, we will use 1 calorie nearly 4.2 joule, like G 9.8 meter per second square to 10 meter per second square. Joule observed that there is a relation. See, you can give heat to a system, or you can transfer heat to a system by two ways. The conventional method is by transferring heat from a hot body to cold body. Like for example, if I want to if I want to cool a glass of water, I have one option. Option one, I can drop ice blocks in that. The other hand, if I want to if I want to heat water, the another option is just add very hot water into the cup of the glass, or else you do some work in that. You stir it repeatedly for hours. Automatically, water gets heated. So, in the form of work also, you can raise the temperature of that water. So there is a relationship between mechanical work and heat produced. And according to Joule, the equivalence is when certain amount of work is done, a definite amount of heat is produced. And the constant of proportionality is called mechanical equivalent of heat, represented by J. This is your famous Joule, right? So calorie undoubtedly is okay, fine, but to be very specific, the specific heat of a substance is defined as the amount of heat required to raise the temperature of 1 gram mass of a body through 1 degree centigrade. Okay? So, which clearly implies whatever the gain or loss you are giving, it depends on three factors: mass, the rising temperature, and the constant of proportionality is what we will call as the specific heat capacity. So it is defined like this: S is Q by M delta T. See, I would like to add another term. See, for example, in some book we will use S, in some book we will use C. Makes no difference. So it is defined as 1 by M dq by dt. That is the correct definition. It is units calorie per gram per degree centigrade inverse. Whereas in SI, joule per kg per Kelvin. Right. See, this is okay, fine. If C is some function of temperature, for example, then total heat transferred, you cannot write like this. You need to write it like this. And that is the reason why we optionally use a word called average specific heat, which is simply defined as heat transferred by m times difference in temperature. This is average specific heat, right? It's like instantaneous velocity, average velocity, right? Most specific heat of water, if you study, it is a minimum. You can see here, it is a minimum around this region. Rare minimum also, it is one at this particular temperature. That is the reason why we will call 14.5 to 15.5, around 15, right? Most of the solids, see, there is a term called most. See, we also introduce another thing, molar specific heat. Molar specific heat. That is also another term which we usually discuss about. That is defined as C is number of moles dq by dt. This is number of moles. This is mass in kg or gram, whatever it is. See, sometimes we will use a term called heat capacity or thermal capacity. It is defined as the amount of heat required to raise the temperature of that body by 1 degree centigrade. If M is the mass, S is the specific heat of the body, then heat capacity is defined as MS. The term mass into S is heat capacity, calorie per degree centigrade unit, or joule per Kelvin in case of SI system. See, sometimes we will use another term called water equivalent, because in CGS system, specific heat of water is 1. For example, you have an object. This is some object. See, uh, I am giving some delta Q amount of heat to this, so that there is a rise of a delta T temperature. Now, this is some solid object, assume. Now, I'm taking water and I'm giving the same quantity of heat for same rise of temperature. Remember, in both the cases, heat given is the same. So, mass of that object solid, specific heat of that solid into delta T is same as mass of water, yes, water, delta T. Strike this. And as you know, SW is 1 in CGS system. So ms, ss is mw. This quantity is called water equivalent of that object. Remember, water equivalent is not for water. You are defining this for some solid object. Right. Next, law of mixture. See, when you are mixing two substance, suppose you are dropping ice into water, or you are dropping a very hot object into the water. So in this, heat transfer might take place from hot body to the cold body. When two substances at different temperatures are mixed, exchange of heat takes place till both of them attain a common temperature. In this, heat is lost by one substance or heat is gained by another substance. Heat is lost by one system and heat is gained by another system. So therefore, suppose if you take this is some system where losing heat. This is another system gaining heat. I'm just giving some simple terminology. And the TM stands for the mixer temperature or equilibrium temperature. Then heat lost, MS T1 minus Tm is MS Tm minus T2. This is the general principle which you will use as law of mixture. The same thing can be used in case of solids, liquids also. Like you have three different liquids, respective masses, respective specific heats, respective temperatures. Now you all mix it. See, there is no loss of heat to surrounding. That is an important word. Here, when you are applying this, there is no loss of heat to surroundings. Right. So in that case, I am assuming one is losing, the other is gaining. And I say that equilibrium temperature is T, for example. See, delta Q is 0 in this case, nothing to the surroundings. So obviously, you will write M1 as for T minus T1, M2 as to T minus T2, M3 is 3T minus T3 to 0. So this part gives you equilibrium temperature of the mixer. Remember, here I just want to add some more points. Allow me to add some more points here. See here, when you are given a combination, it is not possible to do that in air or somewhere else. You will do this in an arrangement called calorimetry. Calorimeter, actually. Okay. See, in this is a simple arrangement of a calorimeter. See, it is you will have some copper, glass, or cup type arrangement. A steering stick made again of copper. This you called as inner space. Usually, this is filled with bad conductor of heat. This is also an insulating ring, insulated ring. See, basically, there is no loss of heat, ideally speaking. And you have a thermometer here. This is a thermometer. So what happens is that, see, you have, for example, M1 stands for mass of calorimeter. Everything put together. Calorimeter. Everything means with the stirrer. M2 mass of liquid in that. And see, when I have written this, correspondingly, S1 refers to specific heat capacity of material of calorimeter. Similarly, as to a specific heat capacity, usually water capacity of a liquid. Remember, initially both are at temperature, say some T1 degrees centigrade. Now everything starts from here. Now you will add some hot object into this and you will stir properly that the temperature is equally distributed or heat is distributed equally, uniformly. Let M3 stands for mass of solid object. Right. And S3, the specific heat capacity of solid, which you have added. And remember, this is at T2 degrees centigrade. T2 is very high when compared to T1. As a result, the entire system comprising of calorimeter, liquid, and the solid added, reach to equilibrium temperature. T equilibrium temperature is some T now. So, using methods of mixture and the principle of calorimetry, heat lost is heat gained. Now see, heat lost. What is the part of the heat lost here? Actually, this is the object which is losing heat. M3, S3, T2 minus T naught. Gained calorimeter T naught minus T1. Water T naught minus T2. Using this principle, you can find the specific heat of the material which I have added. Or you can find the heat capacity of the calorimeter if you know S3. Or if you know S3, if you know the heat capacity of the calorimeter, you can find the specific heat capacity of the liquid in that. Okay, it's a basic understanding. See, my interest now shifted to what happens when we are heating the material. You will see two stages. Now, rising temperature, after some time, uh, change of phase also, like solid to liquid, liquid to gas, likewise. So that amount of heat which is required to change, there is no temperature rise in this process. Change of a phase, there is no temperature rise. Whatever the heat that you are giving, it undergoes for the same state. Does work against the internal energy. It does work against the intermolecular forces, basically. So Q is equal to ml, where L is a latent heat. The unit of latent heat, joule per kg, SI system, calorie per gram, CGS system. See, latent heat of fusion, if you are speaking, solid to liquid, we will use this. Remember, normal atmospheric pressure. Similarly, when you are using vaporization, you are using that water to vapor or steam otherwise. So usually, if not given, for ice, we will use this is the value, and for steam, we will use this as the value. So this is what happens when you heat a material. Remember, x-axis have taken Q. Sometimes they will take T also, time. In that case, the Q becomes power times time, right? So it can be T or Q, because when power is constant, no issues. So I set sub-zero temperatures to 0, then no rise of temperature. Sometime heat will be taken, temperature remains same. In this stage, both ice and water to see. Remember, when ice and water together exists, remember, temperature is 0 degrees centigrade. When steam and water together exists, that temperature is to be taken as 100 degrees centigrade. Remember, all this at 1 atmospheric pressure. So this is how the heating process takes place. Okay. So when we are mixing, care need to be taken. Like for example, I'll just give you a simple case. 5 grams of ice at minus 10 degrees centigrade mixed with 5 grams of water at 30 degrees centigrade. Simple case. So who is the beggar and who is the donor? That I need to check. Now I'm assuming this as my beggar. So first minus 10 degrees to 0 degrees centigrade plus state change. Right. In this, say 30 degrees centigrade to 0 degrees centigrade, even if further required, if it has to give some heat, it will freeze. Remember, melting solid to liquid state, freezing liquid to solid. You heat, solid melts. If the substance rejects some heat out, in that case, it will become ice from water state to ice state. So these are the possibilities. Freeze. Now, what this beggar can demand, see, usually specific heat of ice is half calorie per gram per degree centigrade. Usually latent heat of fusion of ice, usually 80 calorie per gram, just for your information. Better do in calories, good numbers. 5 into half into difference of temperature is 10. Okay, so here it will seek 25 calories. Plus, if the entire ice melts, for example, that requires 5 into 80. 5 into 80, 400 plus 25. So totally, to reach 0 degrees centigrade as water state, this beggar requires 425 calories. Donor capacity. Donor capacity is that if all its heat is lost, 5 into 1 into 30, this is 150. 150 calories. 150 calories. So what would probably happen is that the beggar demands 425 for full melting. After all, the water can give 150 calories. So what will happen at this stage, I will explain. First, this is allowed. इतना तो दे सकता है. 25 calories plus some m dash mass of ice is melting. I am assuming like that. That you equate to 150. M dash times 80 is 125 calories. M dash is 125 by 80. Accordingly, see, 125 80 is not even 2 grams. So therefore, 125 divided by 80 gives nearly 1.56 gram. So finally, what is happening? 1 point ice melted. So finally, you have out of 5, nearly some 3.44 gram ice plus 5 plus 1.56, 6.56 gram water is existing at 0 degree centigrade. This is how you should take account. Similarly, steam and water combination. So that is how you should estimate first. First do the estimation part. Right. Already I have done some problems. These videos are also available for you. I don't know what went wrong. All these things spoiled actually. All these problems I've already done. Only two problems left. I'll discuss only those two. This will conclude what do you call calorimetry, right? So you have a situation here, an ice cube of mass 0.1 kg, okay, at 0 degrees centigrade is in an isolated container, which is at 227 degrees centigrade. The specific heat of the container varies with, I told you a lot of times, not necessarily. There is no guarantee that it should remain the same all the time. Right. You have ice cube of mass 0.1 kg. Specific heat at A, okay, fine, B given. Final temperature of the container is 27 degrees centigrade. Determine the mass of the container. Okay, you had 100 grams of ice at 0 degrees centigrade. It's placed in an isolated container. Okay, fine. The specific heat of the container, no issues. See, you have helped me in giving the initial and final conditions. But the problem is, don't leave it centigrade. 300, 500 Kelvin. 27 degrees centigrade means 300 Kelvin. Right. Mass S dt. This is the last part. And loss is happening from 500 to 300. This is the last part. And whereas the ice benefiting factor is 100 into 80 plus 100 into 1 into 1 into because you have raised it from 0 to 27 degrees centigrade. Here there is no issue. Difference of temperatures. Remember, this is the last part. This is the gain part. How to define gain? 100 grams ice at 0 degrees centigrade to melt first and then to reach 27 degrees centigrade. So finally, the big move in this is M 8 times 500 minus 300 plus B by 2 times 500 minus 500 square minus 300 square is, this is 8,000 plus 2,700. 8,000 plus 2,700. This is 10700. So finally, what will happen in that? By proper solving, you will substitute A value, B value, you will get the mass here, M. You will get the mass of M as 0.495 kg. It's a simple, straight question. Only thing that troubles you is this part. Container of negligible heat capacity contains 10 grams of water at 10 degrees centigrade. Ice is available at minus 40 degrees centigrade. Find the minimum mass of the ice that shall be added so as to freeze the entire water, it seems, not the ice. So the total heat to extract from water to become ice, it is at 10 degrees centigrade. First temperature from 10 degrees centigrade to 0 degrees centigrade. Then entire state conversion. So 100, 800. This is totally 9 or less 10 grams negligible heat capacity, right? 10 grams water, 1 into 10 plus all the 10 state conversion, 80. So 100 plus 800 is 900, right? Right. Now what is happening? The ice mass, I don't know, into 1 by 2 into 40 minus difference of temperature. Initial minus 40, final 0, difference is 40. This is 900. So that mass is 1800 by 40. How much is that? 180 by 4, 90 by 2, 45 grams. Good question. So that's all. I have given all the solutions in the previous video. According to the order, you please proceed.